Okay, Ganesh, can you see this?
Yes, sir. Yes, sir.
Okay, so it's already 2:19. I'll start with the discussion, and after 5-10 minutes, if anybody wants to join, please remind me. So uh, we were discussing the time domain analysis of second order system. So I have shown you one sample example of mass spring and damper, and accordingly we have found four possibilities with respect to the roots of the denominator of second order transfer function. So everyone should remember the standard expression for second order system. So it is given by omega n square divided by s square plus 2 zeta omega n s plus omega n square. So zeta is called as damping ratio. I have just given the mathematical definition for that, which is the ratio of exponentially decaying frequency to the natural frequency. So we discussed about natural frequency and then we kept the damping ratio pending, discussion of damping ratio pending, just for the sake, like, let me complete the discussion about time domain analysis, then I'll get back to the detailed explanation of damping ratio. So that's it. There are four scenarios. One is when the roots are real and different. Roots can be real and different. So this nature of roots is because of the dynamics of the system that everyone should understand. Okay, it's not just randomly obtained, but it's depending on the dynamics of the system, which in turn means depending on the parameters of the system. So roots can be real or different, roots can be complex conjugate, roots can be imaginary, and the roots can be real and equal. So how they behave with respect to unit step input. So all these four possibilities are there with the same system. Okay, for the same system. So how they behave with the different nature of roots, and what is the key parameter that we can identify out of these four transfer functions? Four transfer functions that defines the nature of behavior. So let me proceed. Okay, let me proceed further. So I had left the discussion at this point in the previous class, if anyone can remember. Is it right? Am I right? Okay, that's fine. So that is the question mark as of now. So what I will do is I will make you to understand this concept thoroughly, because it is, as I said earlier, it's a lifelong learning, kind of lifelong learning, because the second order response or the response of second order system is very much important. Only the reason is if we have any higher order system, for example, say if we have fifth order, seventh order, 10th order system, which increases depending on the complexity of the system, they are reduced back to a second order system through some mathematical means. So what I mean to say is, if you have, say, some transfer function which has seventh order, starts in the denominator with s raised to 7, 3 raised to 3 into s raised to 6, 5 into s raised to 5, something like that, we cannot analyze the response of such system for a unit step input through mathematically, because it's a computationally very much complicated. Okay, so it's very much complicated computationally. So for that reason, if you have any higher order system, the key step to analyze such system is using some means of mathematics. Okay, that some means of mathematics is not relevant to you, but just understand there is some technique which helps us to reduce a seventh order system to second order. Means we make an equivalent representation of a seventh order system to a second order system, which governs not 100% of the original system, but at least say 90%, 95% of the original system dynamics. And then we analyze the seventh order system through the assumed or reduced second order system. Then we make a conclusion or design a controller. Then we apply it to the seventh order system. So that's the reason the second order system analysis or the time domain behavior of second order system is very much important. So let us proceed further. So we want to know the response of the system in all these four cases. So what we need to do, we need to derive a mathematical expression to justify this response. So let us hold this sentence for a while. Let us see will how the response will be for these four scenarios. So what one can do to get the response of these four types of system is you can apply inverse Laplace for each of this transfer function. Then you can derive the expression for C of t to get that. Okay, to get that. So let me go in depth. Let me go in depth. So our next objective will be you have to derive some generalized expression for the response of the system in terms of zeta and omega n. In terms of zeta and omega n. So this is quite confusing here. So let me revise or repeat. So those who missed any concept, so follow it again. I said the standard second order transfer function is omega n square divided by s square plus 2 zeta omega ns plus omega n square. And this transfer function is of course obtained through the system parameters, and system parameters may yield us any of these four possibilities. Okay, any of these four possibilities. So what is our next objective is, so out of these four possibilities, I think almost all transfer function will have zeta and omega in it. Zeta and omega in it, except the imaginary case, which is the third case. So this will give us s square plus 9 directly. So this is missing a zeta term, that is the second term, 2 zeta omega ns. So all these uh, transfer functions indirectly have zeta and omega n, or either only omega n. Okay, so our next objective is we need to derive a mathematical expression to justify this response. So how do you derive? Can you derive the expression for each scenario? Okay, can you derive the expression for each scenario and for every transfer function? Does it go that way or something else? So that something else is nothing but we don't derive the response, the mathematical expression for the response for each and every transfer function. Instead, we make a generalized expression for the response which will have zeta and omega in it. Zeta and omega in it. So my wordings may sound a little complicated or confusing. Just hold on for 5 to 15 minutes, you will understand. So I'll make a tabular column. I'll make a tabular column. And in the first column, we write C of S by R of S, which is the transfer function. Okay. So what is this transfer function? It is 24 divided by S square plus 11S plus 24. Okay. So this is the first scenario. So what are the roots of this system? Can anyone tell me? What are the roots of this system? So the roots are nothing but 3 and 8, correct? Am I right? I mean minus 3 and minus 8, sorry. So minus 3 and minus 8 is. Because the denominator you can rewrite as s plus 3 into s plus 8. Please correct me if I am wrong. Can we write the denominator as s plus 3 into s plus 8?
Yes, sir.
Yes. Right? Okay. So this is one type of transfer function in which we have roots as real and different. Fine. S plus 8 into s plus 3 is the denominator polynomial, and we get the roots as minus 3 and minus 8. So they are categorized as real and different. Okay. So how do you identify zeta in this transfer function? How do you identify zeta in this transfer function? By comparing with the standard expression. So this is equal to as good as writing omega n square divided by s square plus 2 zeta omega ns plus omega n square. Okay, can any one of you calculate what is omega n and what is zeta? I mean, everyone please calculate and anyone can tell me. Comparing with the standard second order transfer function, we get omega n square equal to 24. 24. Therefore, omega n is square root of 24. What is the value of omega n? Meenakshi, can you tell me? Chalukya,
Sir, 4.9, sir.
how much?
4.9 omega n, sir.
Okay. Can anyone tell me zeta now? So omega n, is it 4.89? Everyone getting? If anybody is not getting, or if you're getting some different answer, clarify now itself. So omega n is nothing but square root of 24. Then what is zeta? For zeta, to find zeta, when we compare with the standard second order transfer function, at the place of 2 zeta omega n, we have a constant 11. I hope everyone is following this. We don't have zeta directly, but we have 2 zeta omega n. So from this, anybody can get the value of zeta by rearranging the terms, which is 11 divided by 2 omega n. So it is 1.124. Can anyone tell me? If not able to calculate, I mean, if anybody is not able to calculate these things, please let me know now itself. So I hope everyone got this zeta and omega n. Finding zeta and omega n, it's very simple comparing with the standard transfer function. So what is the expression for behavior? We don't know yet. We will keep it pending. So let us do it for 3 more cases. So in the second case, we have only 24 divided by a square plus 24. 24 divided by a square plus 24. So one can directly say zeta is 0 for the second case. There is no 2 zeta omega n as term, but there is only omega n term. So we have only omega n with zeta equal to 0. Anybody can stop me if you are not following. Okay, next. 24 divided by 24 divided by the third case, s square plus 2s plus 24. So omega n is still 4.89. And please calculate yourself, check whether you are getting zeta equal to 0.204. So I made a direct calculation using the same procedure. So I got zeta equal to 0.204. And the last case, which is 24 divided by s square plus 9.78s plus 24, in which omega n is same and zeta is equal to 1. So please note down all these 4 cases. Please note down all these 4 cases. So I'd like to remind you with what objective we are doing this. So our objective is to find a generalized expression for C of t in terms of zeta and omega n, because now everyone can understand how zeta and omega n are hidden or represented in a given transfer function. So we end up with 4 scenarios. So first is obviously real and different, second is imaginary roots, third is complex conjugate. Okay, so if you evaluate the roots, you will get complex conjugate. And if you evaluate for the last one, you will end up with real and equal. So now what you have to remember? You have to remember, when the roots are imaginary, zeta is 0, damping ratio is 0. And when the roots are real and equal, your zeta is 1. And when roots are real and different, zeta is say above 1. And when roots are complex conjugate, the zeta is below 1. Okay, so can you make a conclusion out of it? Yes, it's very simple. So now, if I ask you to plot the behavior, say for example for this transfer function, at this point of stage, you will definitely face a difficulty, because just by taking inverse Laplace and making a tabular column and plotting it is not so easy at this point of stage, okay, for you people. So without that expression, no one can even like guess the shape of the response. Fine. But just for the sake of some visualization or some guessing, I'm going to make some guesses from your side. I will use again a MATLAB software and give you some hints. Just hold on for a minute. I'll open the MATLAB software and show you something interesting. Okay, I hope everyone can see this now. So as we did in one of the previous class, I'll follow the similar steps and I will define a transfer function factor or Laplace factor as s and a transfer function, the first transfer function which is 24 divided by s square plus 11s is written as 11 star s plus 24 like this. So this is our transfer function. So it is showing some value. Sorry, sorry. I missed out something here. S equal to TF of S, then G equal to this transfer function. Okay, now it is clear. You can see it. Right. So let me check how its response looks like before we proceed further. Okay, yeah, this is the response. This is the response. Let me share it. Yes, because it has problem. Yes, this is the response for 24 divided by s square plus 11s plus 24. So this gradually increases and settles down at unity. Okay. So for this case, the value of zeta was above 1. Above 1. And if I mark, say, some characteristics like settling time, rise time, okay, this is for second order, huh? It will give me the values like this. So don't bother about this now. Let us move on to the second case now. Second case where we had a different G. So G was equal to, can anyone tell me what was the transfer function for the second case, or let me take it from my notes. It was 24 divided by s square plus 24. Fine. And let us see how its response looks like. Yeah, it's like it's very difficult to visualize, but let me zoom this. I will share it again, the graph part. So the second scenario where zeta was equal to 0. So this is how the response looks like. So if you zoom this, it is nothing but an oscillatory behavior. An oscillatory behavior. Okay, so let me get back to the dynamics of the system. You have an MBK system, mass spring damper, and imagine you have zeta equal to 0 for that. Okay, so things at this point make some sense. You have MBK system and you imagine zeta equal to 0. Okay, and if you apply some force of unity magnitude, the system behavior, I mean the output of displacement, what you are getting is oscillatory. Are you able to link everything? Okay, I repeat again. I repeat again slowly. You have an mass spring damper system. MBK system, most transfer function I had written, and in that, if you assume zeta equal to 0, the b by m term will become 0. I hope everyone following this, because we had we had s square plus s square plus b by ms. We had s square plus b by ms plus k by m plus k by m in the denominator. So when you make zeta equal to 0, it means obviously b has to be equal to 0 to get s square plus 24, only the constant part. So b is 0 in the sense there is no friction at all. So when there is no friction, it is as good as having zeta equal to 0. Also, if you think practically, when there is no friction, the system will continue to move, and since only the spring is present, the mass cannot move to infinity, but instead it will oscillate around 1. It will oscillate around unity. Is it making sense? Chalukya Bhatt, Ganesh Rai,
Yes, sir.
sir,
Yes, sir.
is it making sense for everyone? Anybody wants me to repeat, please tell it without any hesitation. The second scenario where zeta is 0. Anybody wants me to repeat? Sumit?
Repeat, sir.
Uh,
Repeat it, sir.
okay, I'll repeat it. And Riaz Pasha, are you following? Or confusion? Riaz Pasha. Sumit, okay,
Yes, sir.
Supriya, are you following or any difficulty?
Following, sir.
Following, fine. Okay, one person has asked me to repeat, so others who are not following can also participate here. So we are doing the second scenario of transfer function, which is 24 divided by s square plus 24. We want to know what is its response and why it is so. Okay, so before proceeding with some derivation, we want to know how it behaves and why it behaves so. So assume this transfer function itself is written as s square, sorry, 24 divided by s square plus 24. This transfer function, because of some mbk values, it has given us 24 divided by s square plus 24. So which means we have only s square plus 24. There is no s term in the second case. So we call it as a system with zeta equal to 0, or when you speak with respect to a mass spring damper practical system, we can also say a system with friction equal to 0. Please do not link zeta and friction. I'm making some analogy, just an analogy. So when zeta equal to 0, it equivalently represents a system with friction equal to 0. So when there is no friction at all, we already know that system will continue to move. So I'd ask you one example. Assume a mass block in the vacuum, and if you apply some force, how it will behave or what will be the displacement. Okay. So I hope you can recall that example. So when there is no friction in the vacuum, it will continue to move. But since the presence of spring, which is attached to mass, will make that mass block, instead of moving to infinite distance, will make that mass block to oscillate around certain mean point over infinite time. So this is how it looks over an infinite time. Continuous oscillation. No friction gives us continuous oscillations of air. So my thing is now, are you able to correlate this graph with that particular system? That's it. That's what you have to understand now.
Yes, sir.
Okay. Next. So after this, we'll move on to the fourth scenario. We'll move on to the fourth case where we have complex and conjugate roots. So what was the transfer function? It was s square. It was s square plus Yes, g equal to s square plus, sorry, 24 divided by s square plus, is it 2s? Yeah, 2s plus 24. So what was the nature of roots here? It was complex conjugate. So and what was the value of zeta? It was less than 1. If I am correct, it was less than 1. And this is the transfer function. So let me take the step response of this. Okay, the step response has come. So Ganesh, can you see this response?
Yes, sir.
So this is the response. See here. So it is giving us different response for different type of roots. Here oscillations exist, but they will get vanish after some time. After some time. So the oscillations are not continuing at all. Also, it is not settling down gradually at 1, which was one of the previous case. So zeta less than 1 or greater than 0. You can categorize this particular case as zeta less than 1 and zeta is positive. You have a very sustained oscillations, not continuous oscillations. Okay. And the last scenario, what was g equal to 24 divided by s square plus 9.78 star s plus 24. Any guesses here how the response may look like? Let me run it. Yes. So we got the response. So the last case was when roots are equal and real. This is how it behaves. The unit step response is also gradually increases and settles down at unity. So next thing is we have got 4 different responses for 4 different cases of roots, the denominator roots or the poles or the characteristic equations. So just give me a moment. Okay. And the last case was when theta greater than 1, we had this situation. Right? So can you look at the 4 different types of response? One is continuous oscillation when zeta was 0 or there was no friction. Very sustained or very less number of oscillations when zeta was less than 1 and greater than 0. And there was no oscillation at all. There was no oscillation at all when zeta is equal to 1 or greater than 1. There are 4 systems, 4 different types of response. Fine. So now the next objective must be very clear. Okay, since we are making a fundamental study of control systems, so we are studying the fundamentals. Our next objective is to understand why do we get this type of behavior or how do we get this type of behavior and what justification we can produce so that one can say when zeta is 0, this is how my response looks like. Or when zeta is greater than 1, this is how my response looks like. Okay, so it's very clear. Or in other way, one can ask me directly, sir, the software is doing all these things. Why we need to understand or study this part? It is anyhow executing and giving all the data. Okay, but the thing is, the background, what runs at the background, we should study it now. Okay, So that's what an engineer has to understand. Software is just a tool. Okay, many available, readily available functions can be used to produce the result, but what runs at the background should always be understood by an engineer. Then only we can produce some new things. That's what I believe. So next objective is what we need to do is what we need to do is what is this C of T expression that justifies all four types of behaviors. That justifies all four types of behaviors. So it's not so easy as compared to the first order scenario where we derived C of T very easily. Here we need to do some additional things to prove that. So everyone understood what we're going to do next? Anybody not understood what we are going to do next? Please understand and then we'll proceed. Any doubts till this point? Any clarification till this point? So as I said earlier, few things I'll repeat in this chapter because I want to everyone to follow. So now I'll make a final table and I will write everything with respect to zeta instead of nature of roots or transfer function. So now I'll just shift the table and write the first case when zeta is equal to 1. We know roots are real and equal. So type of response, whatever we had got using the MATLAB for zeta equal to 1 is called as critically damped scenario, critically damped case. Next, when zeta is greater than 1, we got the roots as real and unequal, the -3 and -8 case. We call this type of behavior as overdamped case. And when zeta is equal to 0, we call it as undamped, sorry, it is imaginary roots and the type of response is called as undamped case, third case. And the fourth one, when zeta is between 0 and 1, which is positive, we call this as complex conjugate, and this particular type of behavior is called as underdamped scenario. Fine. Anybody not understood this table? Like why real and equal when zeta equal to 1? Please go back and refer to the immediate previous discussion. So now we are moving towards making generalization. Okay, first I consider an example with a numerical, the number. Then I shown you that those transfer functions are related to zeta and omega n. And now to make more generalization with respect to zeta and omega n, I am making this column. So with respect to zeta, there are 4 types of behavior. So that's what it should be clear to everyone. So this flow I particularly highlighted, this lengthy introduction is most of the textbooks without showing you why the 4 cases arrive, they directly start the derivation. But I feel you should know why these 4 cases arise before making any derivation or deriving a mathematical expression. So that's it, friends. And okay, so that's it. And immediately we'll start the derivation now. So 4 cases. So what is our case 1? Case 1 is zeta equal to 1, where roots are real and equal. Where roots are real and equal, and it is called as critically damped case. So when I say critically damped system, your mind should immediately recall the value of zeta equal to 1. So what is our objective here? To derive expression for the response C of t Yes, somebody has question.
Yes, sir. Sir, in the previous example that you're taking,
Mm-hmm.
uh, the equation, the last, when zeta is equal to 1, that equation, sir,
Mm-hmm.
24 by x square plus 9.78 s plus 24. So the roots that you're talking about is in the denominator side, right, sir?
Yes, obviously.
Yeah. So, sir, in that part, s square plus 9.78 s plus 24, I'm getting a
Hmm.
complex conjugate root. Can you just check, sir, once?
Complex conjugate you are getting, you shouldn't get that. Uh, okay, let me check for a minute. Remaining also, please cross verify once.
Yes, sir, it's conjugate, complex conjugate.
So that's fine. Let me check. Let me check. Sometimes it will show the complex part with a very less value. Okay, sorry for that. Okay, sorry for that. I think I have missed something there, but it shouldn't be complex conjugate. So is that clear to everyone? So I made a mistake in that last situation while giving one numerical example for zeta equal to 1 scenario. Okay, this was zeta equal to 1 scenario wherein which we should end up with real and equal roots, but it's my mistake. We are ending with complex conjugate. Please, I will give the other example. I will correct that while uploading. Okay, fine. Okay, is it fine? Those who raised query.
Sir, then how about the response that you're getting is same, sir? Like zeta
Hello.
is equal to 1 and the graph that you made the MATLAB. Like it didn't give the complex conjugate, the previous example thing. That kind of graph, sir, oscillating.
Okay, 24 divided by what was that? S square plus 9.78
S plus 24.
s plus 24. Yeah. What happened? It didn't give us.
Sir, the graph that you made on MATLAB, sir,
Mhm.
that wasn't oscillating graph. It just touched 1. Whereas
Oh,
the
yes. Whereas roots are coming as complex.
yeah, and the complex conjugate, that graph that you showed, it was oscillating like till a point and
Yes,
then
yes,
it was damping. Why is it
yes.
happening like this?
It's happening because there are the imaginary part is very less as compared to the real part. So our zeta may be nearer to 1. We may get maybe nearer to 1. You can cross verify.
Sir, but isn't the division a little weird then? Like the way you're dividing it currently, according
It
to
is.
zeta 1 and this thing. Zeta 1, zeta greater than 1, zeta equal to 0. So,
And
so according to that only we are getting the graphs differently, sir. The division, the way we are
correct.
dividing
Correct.
it.
Yes,
But
correct.
if the roots that we are getting both are complex conjugate and still the graphs are different, sir, then the division that we did right now is, I feel it's a little weird. Like the division should be in some other way.
Okay. It's not in some other way. It's not in some other way. Mm, why am I ending with C? Uh, okay, how to explain this? This point is also challenging. Okay, listen to me carefully. Um, you forget about this 9.78 example as of now. Okay, just I'll solve it definitely. What you are asking is we are getting complex roots, but our behavior is different. Fine.
Yes, sir.
It has an answer. It has an answer, but if I tell it now, there is a possibility that everyone will get confused. So avoid that example as of now, and let us take an example of 36 divided by s plus 6 into s plus 6. Simplest. So zeta equal to 1 case, let us take an example of 36 divided by s plus 6 into s plus 6. Correct? So if you take this, will you end up with zeta equal to 1 now? I repeat everyone to follow. Take a new transfer function for zeta equal to 1 case, because your friend have highlighted one query with that. It has an answer and I'll answer it soon in the next class. Definitely I'll answer. So for time being, take zeta equal to 1 case as with this transfer function. Okay, the one who is asking query, whether now zeta is equal to 1 for this case? Because omega n is 6, 2 zeta omega n is equal to 12. So you should end up with zeta equal to 1. Ganesh, can you see the screen?
Yes, sir.
Yes. So I will convince you that with zeta equal to 1 you will get the response which I had told earlier. Okay, so can you see this now? I just want to know the name who had raised query, please.
Sir Abhijit.
Abhijit, yeah, it's visible?
Yes, sir.
Graph. So this is for 36 divided by s plus 6, s plus 6. Fine. So Abhijit, zeta equal to 1 will give this type of behavior only.
Okay, sir.
So forget about the previous contradictory example. And now you convince yourself if zeta is equal to 1, this is how it behaves. And I will answer that question soon. Fine?
Fine, sir.
Fine. Okay.
Sir,
Yes, huh?
sir, in the previous, the complex conjugate example, if
Okay.
you change the scale of the graph, we would be able to observe the oscillations, right?
No. You can observe the graph very easily. Okay, let me share it again. There's nothing difficulty I have. I will share it again. So you want the graph for complex conjugate scenario, right? Z
Yes,
equal to 24 divided by s square plus what was that? 2s 24. Okay, there is star missing. Oh, sorry. Shift it. Oh, sorry.
sir. Sir, I
Okay.
meant the 9.781.
Okay, 9.781. Huh. 9.781.
Yes,
That's
sir.
what
In
I'm
that,
telling. It is giving complex conjugate. Okay. So you mean to say there exists oscillation? We have to zoom it.
yes, sir, because if we take the poles, we'll have, if there's a real part and an imaginary part, and like even for Fourier transforms, when we plot the poles on the imaginary axis, it denotes the oscillations, right?
Yeah, obviously. Okay, so
So I just wanted to,
oscillations are not visible here. Oscillations are not visible here even after zooming. I'll answer it if you can hold. What's your name?
Meenakshi, sir.
Meenakshi. I will answer your query and Abhijit's query
Okay, sir.
that your question is no, though we have complex conjugate, why we are not getting oscillations in the graph? Okay.
Yes, sir.
So
Yeah.
ultimately we are moving towards that only actually, indirectly. So now forget everything and critically damped case zeta equal to 1, 36 divided by s plus 6 into s plus 6. So for this, we should know why the response was like that, why it was gradually increasing and settling at 1. That we have to derive now. So we start with the from fundamentals. We know that the standard second order transfer function is this s square divided by for omega n square divided by s square plus 2 zeta omega n into s plus omega n square. And now, without any doubt, I will substitute zeta equal to 1 and rewrite the expression like this. So this is a given system where we are ending with zeta equal to 1. So I can rewrite all mathematical steps here. Please copy this or just observe carefully. So s square plus 2 omega n s plus omega n square we have, then omega n square divided by s plus omega n into s plus omega n or omega n square divided by s plus omega n whole square. Fine. So next we have to write expression for C of s for a unit step input applied. So I'll keep this as it is, take R of s on the other side. So R of s is 1 by s because it is unit step input. So now C of s is equal to this expression into R of s input. So R of s is unit step function, which is directly 1 by s. So what is C of t for this now? So that's our next goal. Let us proceed with this above expression. So we have to take inverse Laplace transform now. To find C of t, take inverse Laplace transform of, say, this equation or equation 1. Equation 1. So how to take that inverse Laplace? Simplest way is, I prefer partial fractions. If anybody knows anything else, can try out. There is no restriction that strictly you need to follow my method. So the simplest partial fraction can be done in this way. I will define three constants, A, B, C. Anybody can stop me if I'm going wrong. I mean, if I made any mistake of the A, B, C, yeah, fine. This is using partial fraction. Diploma students, please concentrate and revise partial fraction if you are not aware. So then I will simplify. So A, okay, yeah, S is missing. A into S plus omega n into S plus BS plus C. So taking the common factors in the denominator, then equating to LHS. So the easiest thing is substitute S equal to 0 in this expression. We end up with the LHS part as it is. This S is multiplied here with all the terms, so it is 0. B into 0 is 0 plus C into 0 plus omega n square. So solving this, we get C equal to 1. Then we don't know the other way, so we will have to substitute S equal to 1 to get A and B. So when you substitute S equal to 1, this is 1 plus omega n into 1. So A plus A omega n plus B plus C is 1. So 1 plus omega n whole square. So 1 plus omega n whole square. Then S equal to minus 1 here. There's a minus 1 and minus 1 is plus 1. So plus A minus 1 omega n is minus A omega n minus B plus minus 1 plus omega n whole square. This is just substitution. I hope there shouldn't be any difficulty here. The next is just add both of the equations. Our job is to cancel out one of the unknown to find the other unknown. This is the easiest way to add and cancel B. So we get 2 omega n square, 2a, this and this will cancel, B will cancel. If you simplify and add, you will get 2 plus 2 omega n square. So and check out whether you are getting A is equal to minus 1. I will hold for 2 minutes. I'll hold on for 2 minutes. So if anybody has no difficulty, I need 15 more minutes. 10 to 15 max. If anybody has any difficulty, can tell me, I will wind up. I want this to be completed. Few more steps. Not much, few more steps. So please bear with me. Anybody got A equal to minus 1? Can do in your own way. So let me show the answer for B also, then you can cross verify. So for B, I am subtracting each other. So it will start with 0 equal to subtracting both of these equations. So the sign will change for all these elements. So minus omega n square 0. Then A will become 0. Then this will become 2a omega n, because subtraction of minus means it will become plus 2a omega n, where a is minus 1 already known, plus 2b, and if you subtract these two terms we get 4 omega n. This implies again 0, substitute the value of a, so it will become minus 2 omega n plus 2b plus 4 omega n. So this 4 omega n and 2 omega n will cancel out. So we have, okay, 4 omega n minus 2 omega n is plus 2 omega n taken on the other side, minus 2 omega n. 2 and 2 will cancel. We'll end up with b equal to minus omega n. So should I wait for 2-3 minutes? Puneet VH, are you following?
Yes, sir, fine, sir. Following.
Are you able to calculate ABC constants, Siri, MS? Any difficulty?
No, sir.
Okay, just let me cross verify with the two more. Nadeem,
Yes, sir.
Nadeem, following. Mohit Gowda.
Yes, sir, following.
Okay, then I hope everyone is following. So proceeding further, after finding A, B, C, so A is minus 1, B is minus omega n, okay, sorry, C is 1. I missed out negative sign. So I'll substitute all ABC and this is how we end up with. So minus omega n, okay, I have considered minus here. So ultimately we have C of t equal to what is the Laplace inverse of this? Very simple. E raised to minus omega n t. What is the Laplace inverse of this denominator? We have a square here, whole square. So keep omega n as it is. So when you have whole square, it is t into e raised to minus omega n t. So this is a there is one Laplace inverse identity we have. If you have 1 divided by s plus a whole square, its Laplace inverse is t into e raised to minus at. T into e raised to minus at. So that's how it ends. Omega n was already existing, so keep it as it is. In the last term, 1 by s is 1. Last term is 1 by s, which is 1. So this is it. That's the derivation. That proves why the graph was like that. Or rearranging, we get 1 minus e raised to minus omega n t is common. And it is 1 plus omega n into t. Okay. Into t it is, not of t. This is critically damped behavior. Critically damped behavior. Expression for critically damped behavior. What's the next step? Let us plot. Sorry. Next job is let us plot this for critically damped case. So how do you plot? Suppose there was no computer existing and you had to plot the response. What is the simplest way? You plot xy axis. X axis goes to the independent variable t and y-axis goes to the output C of t. So make two columns. C of t equal to 1 minus e raised to omega n t into 1 plus omega n into t multiplied by t. Okay. So the other unknown is omega n. I can assume some value for omega n, some relevant value which comes from some dynamics of the system. So I will assume the natural frequency of some dynamical system omega n equal to 2 radians per second, and I will substitute it in C of t and just plot the graph. So let me assume the t values 0, 0.5, 1, 2, anything, 5, 10, 1000 and even infinity. I will assume infinity, t equal to infinity. So what is C of t for t equal to 0? Can anyone calculate? So when t is 0, what is the value of C of t? Anybody can tell me?
0.
0. Because 1 minus e raised to 0 is 1 and here t is 0. So this 2t is 2 into 0. So it is 1 minus 1 into 1 which is 1 minus 1 equal to 0. So I want to calculate for 0.5 next. When t is 0.5. When t is 0.5, let me calculate. I'll write 1 minus e raised to minus 2 into 0.5 to 0.5 into, okay, let me write it in another way. Okay, let me write it in another way. And first calculate e raised to this part, multiply that with 1 plus 2 into 0.5 and subtract this from 1 minus answer. So this is 0.26. Please calculate yourself without fail. I may be doing mistake sometimes. So for 0.5 it is 0.26. Next for 1. For 1, what is the answer when t is 1? I'm calculating again. So I'm writing everything to show you clearly. So when t is 1, C of t is 0.59, more than the previous value. Everyone following how to calculate? So if you continue, and suppose, let me calculate the value at say 1000, t equal to 1000 seconds. T equal to 1000 seconds, e raised to minus 2 into 1000 is showing me 0. So this term is 0. So 1 minus 0 is 1 only. At 1000 seconds, our output is reached to unity approximately. So at 1000 seconds, our output is unity. Fine. So this is how it looks like, gradually increase. This is approximated graph. Please understand, I have not calculated over all the range. So this is our output and this is our input. Input R of t equal to 1. So now, are you convinced that whatever graph we had seen for 36 divided by s plus 6 into s plus 6 is because of this expression? Are you convinced for that? If you replace omega n equal to 6 and calculate everything again, you will end up with the same nature of graph. Same nature of graph. Fine. So this is how it goes. Abhijit, is it clear?
Yes, sir.
And the other girl who had asked another query, is it clear for you also?
Yes, sir.
Okay, and others. So now we are convinced that at the background of the software, this is what goes, this tabular column. Okay, so whenever I write, say, the step response for this particular system, at the background, it will automatically make a column or calculate Laplace inverse and substitute zeta omega and make a table and plot it. That's what will be written at the backside of the function. Is it clear? Any doubts, any queries? So next job is to show this for other 3 cases. That's it. To show this for other 3 cases, that is to find C of t for other cases. And it is not same as this, obviously, because we have complex, real, different, imaginary roots. So there is a different